Good afternoon, good evening, and good morning. Greetings from Stanford University, and welcome to the 27th AEC Global Teamwork Final Project Presentation Cyber event. My name is Renate Fruchter, founding director of the PBL Lab, and your host for the day. The PBL Lab is the home of the AEC Global Teamwork course I've been teaching since 1993 with partners worldwide. Our vision is to transform our students' tool set, skill set, and most importantly, mindset, moving from working in discipline silos to work as a single, cohesive, interdisciplinary team and develop fully integrated solutions. Our aim is to prepare the next generation leaders and change agents for the future workplace and challenges that they will encounter. What is unique about this class is that it brings together students, faculty, and industry mentors from 5 disciplines: architecture, structural and mechanical engineering, construction management, and life cycle financial management. Students learn to collaborate in globally distributed teams to virtually design university buildings, addressing local hazards such as earthquakes, hurricanes, flooding, local labor conditions. I have to say, this year has been a great pleasure to mentor and work with highly motivated, creative, and committed students from Stanford and 12 university partners worldwide. Given the unprecedented COVID-19 challenges and shelter in place, we are organizing this annual event in cyberspace rather than having everyone back at Stanford for a final great, engaging celebration. In preparation for this year's May 8th cyber event, we had to be creative as we are all geographically distributed over 8 time zones. For this purpose, each global student project team prepared a video story of their project evolution. These stories were reviewed and assessed by 30 industry mentors prior to the May 8th event. I have to say, we miss everyone back at Stanford for this event to celebrate the end of the AEC journey together. Nevertheless, we are really excited to see today at our May 8th final presentation Zoom live cyber event a great turnout of 89 participants that includes the global students and 57 industry and faculty mentors. Each team will present a TED-style project team pitch to give everyone an overview of their proposals, followed by a Q&A discussions of their concepts. But before we dive into very exciting student presentations, I want to extend a big thank you to our industry and faculty mentors, alumni, and owners and sponsors who so generously dedicated their time, attention, and knowledge to our AEC Global students. In collaboration with industry partners, we defined 3 challenges to further foster the students' creativity. Focus on sustainability, specifically this year, resilience, integrating project delivery, focused on the question whether to industrialize or not to industrialize, as well as shared risk and reward, and technology innovation focused on intelligent interoperability between models and disciplines. Winners will be announced at the end of the cyber event, May 8th. So don't forget to visit the PBL Lab Project Gallery website to find out who this year's winners are. Last but not least, a special thanks for the generous support of our technology industry partners that enable us to continue to develop new ways of working and learning by leveraging the latest emerging technologies like VR, virtual reality, AI, artificial intelligence, parametric modeling and optimization, and embed them in the students' new daily work practices that they experience in this global teamwork class. And with that, let's move on to the student presentations.
That's great. So, hi everyone, we are Team River. Our group consists of Ida, the architect, Yanne and me, the structural engineers, Koske and Mina, our construction managers, and Julius, the lifecycle financial manager. Our site is located in Weimar, Germany. The area is a UNESCO World Heritage Zone combining beauty and history, with a lot of beautiful old buildings towards the city in the west and the big park with the Ilm River to the east. We have to fit into the surroundings and beware the site. We investigated the context to get inspiration for our building. We want to relate to the castle with its tower, the university building, and the bridge. We dealt especially with the materials, wood, copper, and cobblestone. In general, we learned that the city has a geometric typology, which we also want to achieve in a modern way. We are facing a lot of constraints we had to consider in our design process, such as flooding from the river and the slope on the side. The existing chestnut trees were wished to be preserved. Additionally, we have a narrow construction site and streets. Our goal is to achieve all three types of sustainability, and we want to do that by focusing on the users, being energy efficient, and implement flexibility. Furthermore, we got the three challenges: resilience, DPR, and IT, which we of course aim to win.
So what are we designing for? We are designing for the users to thrive and learn in an innovative student environment. We are designing to respect and give something back to the context in Weimar. We are as well designing for the building to sustain any changes according to the unexpected events in the future, and also to create the possibility to give the building life again with the needed purpose of a future day. From before the window presentation, the design evolved from the concept Buttercup. And here you see our Buttercup building. The Buttercup is this flower that constantly relates to the sun and shapes its petals, so a warm and pleasant spot is created in the center. This is the reason why the Buttercup is super attractive to the insects, embracing them as our building should embrace the occupants. The design evolved from the inside of the building to the outside. First, we created the connection from the park to the river, which we felt was necessary to make the insects explore the best features of the surroundings within the building. Then a cantilever was created between the architect and the structural team. The atrium was created to have a warm and bright core for gatherings of the insects and to let in the daylight. The facade is a fusion of prefabrication, architectural expression, daylight, and heat gains.
At the first floor, we locate more public rooms and social rooms, and we are having classrooms, auditorium, and a cafe here. On the second floor, we have some more workshop areas and group offices for the students. So this is mainly the floor for the students to be. On the 1.5 floor, we have a big collaboration and flexible area and two big, large classrooms. And this place is ideal for the student presentation and creative work. On the third and the last floor, we mainly have space for employees. And we utilized a few square meters from the offices to create some collaboration areas for socialization. We think that socialization is the key to achieve a creative, innovative, and collaborative work environment. And we created a nice break room with space for all the employees and a flexible space to work or to have a casual meeting.
Our structural framing is designed mainly in timber, as you can see. We have a concrete floor and 2 cores with CLT walls. What I like to point out here are 3 special features or places in the building. First is the left side of the building where the auditorium is. Those dark lines on the plan represent the post-tension beams we put there. Then on the part of the large cantilever, we also have large beams which are continuous and provide backspan. Trusses where we work together with the MEP are mostly located in the common areas in the north between grid line A and C.
The primary systems in the building is a heat pump connected to solar panels on the roof. The building is mechanically ventilated through air handling units, and a water loop is created with rainwater harvesting on the roof. All the rooms have VAV controlled ventilation. The large volume rooms are provided with displacement ventilation, are natural ventilated through April to October. All smaller roofs have diffuse ceiling ventilation. Now we will welcome you into our Buttercup building through a VR tour.
So this is the main entrance of our building, and you see our west facade here, and it consists of some different elements. We are having this grid, which is the architectural expression that we want from the city, and it's also due to the prefabrication on our facade. We have these change on the facade, which is to protect the wood on the facade from the rain. And we will have some ivy plants that is going from these cover changes, and they are inspired from the tower of the Weimar Castle. We are having these louvers on the facade, and they have a different expression on all the different orientations, and they are due to reduce heat gains. Let's go inside the building. So here you see how it looks when you enter the building. And now we will go to the atrium. And the atrium have a lot of different purpose, so we can rent out the space. We can both have it as a stage area in the summer. We can have a regular lounge as now, and also use it for presentations. Let's go to the cafe. In the cafe, you can, as an occupant, eat your food, and you can also buy some food. In this area, it's really visible that we're having some flood protecting walls towards outside. They are only activated when there's a third stage flood, and they protect us from the water when the water rises. Let's go to the auditorium. The auditorium is a room that is really future-proofed. We are having a lot of different technologies that improve the study environment for the students. We are having some smart boards. We are having completely good acoustics. We are having some sound screens, and we are having some tinted glass. And as you see in the ceiling, we are having post-tension wood structure, which is really good for this large span. And we are having a really symmetric MEP system. And upstairs, we're having the large classrooms, and we're utilizing the architectural height here by putting these two rooms on top of each other. As you see here, you see the louvers, they're different on the different facades. So in south, we are having the louvers horizontal, and in the west, they are vertical. And outside the large classroom, we are having a collaboration area that we're calling the swing area. And here we also have the post-tension wood, and therefore we have this large span and no column, so you can collaborate here. And this bench we're having is to cover the displacement ventilation duct. Let's go to the labs, which we, together with the owners, actually interpret the space for the labs differently. So we did one big workshop area in the building, and we put some flexible furnitures. So for the future use of the building, you can move the chairs, the tables, and these dividing walls into a big storage room. We're having a storage room instead of a server room because we have cloud service. So therefore you can completely transform the whole space of the building. If we go out of the room, we can show that we are having some student offices outside here. And in the future, we really want to adapt to giving shelter. Therefore, our building can transform to a hospital. So as you see here, one of the main offices is turned into a hospital isolation ward. And our whole building can help the community in case of a pandemic in the future. If we go upstairs, we will go to the top floor of our building, or third floor. And here, this is mainly for the employees of the building. And here we also have offices, and we are having a collaboration area outside the offices as an And you see in the ceiling, in this part of the building, we are having some wooden steel trusses. And the reason why we're having that is so the MEP can be integrated with the structure, and therefore we can reach a pleasant architectural height and still have 3 floors here. So our architectural height is 2.83 meters high.
Good.
In this section, you get a quick summary of the parts that makes the whole Buttercup project. We have the different flood protection implementation from the bottom level of the building to the roof. You also see some of the spaces where the disciplines had to work closely together to create a well-functioning building with room for well-being. As we experience right now, and as it has occurred for centuries, extreme situations can suddenly strike without any prediction. That can be due to pandemics or climate changes. That is why we felt the necessity to embrace new ways of thinking in terms of being reactive and predictive to the future when we were designing our building. In our design, we aim to make it as flexible as possible to easily respond to the changes that will affect a whole population now and in the future. Large building as university has the possibility to create space for beds and shelter in this situation. This graph shows how fast this need can escalate. When people feel sick, they can come and get a test at the university and be taken care of in the right settings. Our Buttercup building should be a place for recovering and well-being of affected insects or occupants.
So we have to make sure that we are separating the patients between the stage 1, that is testing, stage 2, care in the patient ward, and stage 3, sick in isolation or step-up care. The test area is in our auditorium, and this is where you have direct access from the outside. The cafe will be utilized as the kitchen. A patient ward will have 10 square meters for each person, and it will be located in the 1st and the 2nd floor. As further you move up in the building, as more isolation room do we have. The 1.5 floor is utilized for the staff because you cannot have a hospital bed here, but you can have a wheelchair user. On the top floor is the most sick people, and they are in the isolation rooms.
To be able to fulfill the ambitious hospital requirements, we created flexible ducts that are more movable and allow flexible ventilation. The installed VAV control allows a negative air charge rate. With an installed HEPA filter, we can ensure that germs are not transmitted through the HVAC system during a pandemic. In times when the building is used as university, this is also helpful during flu and pollen season. We have easy to clean surfaces all over the building and hand sanitizing stations in our building to ensure a healthy environment for hospital and universities. We are a private-public partnership. In our case, we construct a university building and operate it in exchange for an annual rent. But are we also a hospital? As discovered recently, the building can't be used as university during a pandemic. In this case, we will hand over the building to the public health system. This helps us to compensate the loss of rent from the owners and to cover the peak demand for hospital space.
We also calculated the number of days it would take for an emergency transition to hospital. Since there's no need to change the room layout, most of the work will be MEP works, but since necessary MEP works are already designed to work at the time of construction, the work can be minimized and completed within 2 weeks.
So moving forward to how this building will actually happen, as a reminder, our building just fits into the site and there is no space on both the east and west. So after considering all our constraints, we generated the schedule using Alice and found the optimized schedule that has the minimum cost and time with the maximum utilization. We also use Alice along with VR to pinpoint the construction peak flow. So on October 14th, we found that there are 3 activities occurring at the same time and that require hosting 4 equipment at a time. And due to our constraint side, that would create a bottleneck. So we plan to push one of the activities that doesn't lie on the critical path. So after adjusting our schedule, we import into Fuser that will generate a 4D construction schedule.
On the left, we see a chart of our TBD and STB evolution from winter till now. Our final TBD is at 7.7 million, which is 500,000 below our original target. As we started our TBD journey, we had neither exact cost data nor materials or quantities. On our way, we had major design changes, but also improved our cost data thanks to a German contractor called Beck, who was friendly enough to give us access to their cost database with real project data. Our STB data changed as well as major design decisions were made. On the right side, you can see the lifecycle cost distribution as shown. It developed from TBD and STB data. Over the lifespan of the contract, the building associated costs are around 90 million euro. All our financial targets are well covered.
Besides transforming our building to hospital, we also considered flooding as a place where to be resilient. Due to future climate change, we expect drought in summer and increase of flash flood risk in winter. How can we prepare on all of that, and in which system we should invest the most? We say that having redundant modular system that benefits to users and can fail safely. Our response has 4 stages that protects property and helps the building during daily operation. Stage 1 and 2 as SUDs on the roof with local vegetation helps us with reducing consumption of water. Landscapes helps us protect our building from minor flood. For stage 3, we are using reinforced concrete walls with lift flood walls that helps us in case of 200-year flood. And stage 4, with right selection of materials and MIP protection, help us to be safe from extreme events to reduce disturbance in operation phase. We choose our response to benefit building users, local ecosystem, and to increase performance of building with redundant response.
This is a summary of how we tackle the DPR challenge. We assess the risk and reward using 11 criteria spanning over 5 categories. We assign different weights according to their significance. For example, we assign high weight to cost and schedule reduction and give less weight to others. We studied 5 items. The main target beyond our selection was to minimize the construction process or site where there is high cross-disciplinary integration. We have other risks to mitigate, such as transportation problem to such a restricted site and the increase of material cost. We studied industrializing the facade modules, where each module is broken down into kit parts using Kit Connect. The size and the layout of the facade module were optimized to standardize the number of panels used. It's worth mentioning that the facade module in the first floor under the cantilever was not manufactured off-site due to the difficulty of installation on-site. We also studied unitizing the roof to reduce the amount of dirty work during the finishing stage of the roof. We chose to have the roof panel to be manufactured off-site and the solar panel will be installed on-site. We also did a study to prefab the toilet box, where all the finishes and sanitary fixtures will be installed off-site and will be delivered as a box during the structural work. In addition to a study where the floor panels are optimized according to the crane location and cost. Last but not least, the flexible walls are planned as pre-finished assembly to minimize the amount of installation of work.
Here's a summary of what's relevant to IT challenge. We use available software to interpret on several items from each discipline. In particular, the facade design was examined in a wide range of areas from visual analysis, shape, performance, cost, detail dimension, schedule, and construction method to create an optimum design. Also, MEP and structure design interpret size of duct and beam, performance, and
It's okay.
Lost IT.
Of construction to, can you hear? Can you hear me?
Now we
Yes.
can.
Yes, you are back.
Okay.
Go ahead.
Okay. Structure system coordinated parametric analysis of construction to find the best design and plan. We created a digital overall pre-planning at the beginning and converted to Asana tasks. This allows us to proceed efficiently with each individual task. Dependency of each discipline significantly improve in the sprint quarter by knowing what others really need. Degree of centrality become well balanced and resulted our great project. Working time record clearly show increasing meeting time, reduce the rework rate, particularly after we started stand-up daily meeting. Asana task record shows 411 tasks were completed in 2,500 hours total. We believe this project turned out to be an invaluable experience for our career. Throughout the project, we learned that a project is never completed by one person. We also experienced that the distance can be shortened by technology, and it will not be an obstacle for our generation. We thank all our supporters for the project, owners, mentors, and some additional supporters from the industry. With this, we conclude our presentation, and thank you all again for being with us.